Okay, 15.7, part 3. For this one, we're going to do example number 2 on page 1113. So let Q be the solid region between this paraboloid and the xy plane. This paraboloid, okay, 4 minus x squared minus y squared, so we're going to be at 4 here. Opens down, makes a circle in the xy plane with a radius of 2. Okay, so this is our paraboloid, made up of two surfaces. We'll call this one S1, and this disk on the bottom is going to be S2. Okay, so we have to verify the divergence theorem, which means we have to show that it actually works. The divergence theorem says the double integral of f dotted with n ds is equal to the triple integral of the divergence of f over the volume. And this is over that region Q, and this would be over the surface. Okay, so this is really the flux through the surface. When it's a closed surface, the flux through the surface is your outward flux. So up top, it's going to be pointing upwards, and this disk on the bottom, it's going to be pointing down the normal. Okay, so this we have to split into two surfaces. Double integral of f dotted with n ds on surface 1 plus the double integral of f dotted with n on surface 2. Okay. So this first surface is this one up here. Let's do this. We've got f. The vector field is 2z, comma x, comma y squared. Dotted with this. Now remember what this normal is. Normally the way we find this normal for a surface, we do RU crossed with RV to make it a unit normal, unit vector. We go over the magnitude of RU cross RV, and then du dv. Okay, in this case, we're going to use the simplified version because our function z is a function of x and y. So we can use the simplified version. This is opposite of dz dx, opposite dz dy, and 1. So we're going to do that here. dz dx is negative 2x, the opposite of that is 2x. dz dy is negative 2y, opposite of that is 2y, and comma 1. Then dx dy. Doing this integral, we've got 4xz plus 2xy plus y squared dx dy. Okay, now let's do this one over here, which is the second surface, which is going to be plus the double integral of f, same vector field, 2z, comma x, comma y squared. But the normal to that surface is just the vector pointing down. So 0, 0, negative 1. Okay, dx dy. So conveniently, we've got double integral 0 plus 0 and then minus y squared dx dy. Now, normally what you might have done here, you'd see that the region in the xy plane is the circle with a radius of 2. So we'd turn it into polar coordinates. And yes, you would be correct. We normally do that. In this case, we're not. This problem's a bit contrived. I just tried doing it with polar coordinates. It got really, 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 really messy. Here's my work. It got really messy. And instead, I'm going to show you something really neat happens. Things simplify quite nicely. If we do this, if we leave it in terms of dx dy. Okay. So now we've got this function, double integral of this function plus the double integral of this function. Notice this plus y squared and this minus y squared. If we combine it into one double integral, that goes away. So we've got a double integral of 4xz plus 2xy dx dy. And now we'll call this 4x times z. Our z is this function, 4 minus x squared minus y squared, plus 2xy. We need to do that because we need to get everything in terms of our differentials, dx dy. Okay, so double integral, that's going to be 16x minus 4x to the fourth minus 4xy squared plus 2xy dx dy. Okay. X is going from, remember this circle here in the xy plane, x squared plus y squared is equal to 4. So x is equal to plus or minus square root of 4 minus y squared. So we've got negative red 4 minus y squared to positive red 4 minus y squared, and then y is going to go from negative 2 to 2. Now watch what happens, which is really nice here. We're going to integrate with respect to x. So 16x squared over 2, that's 8x squared. minus, sorry, this is not 4x to the fourth. That was 4x times negative x squared. That's 4x to the third. So we get minus 4x to the fourth over 4. So that's just going to be minus x to the fourth. And then here we get minus 4xy squared. Minus 4x squared over 2 times y squared. So that's just going to be minus 2x squared y squared. And then plus x squared y. We're evaluating from negative red, 4 minus y squared, to positive red, 4 minus y squared. Let's plug this in for x. So that squared, we're going to get 8 times 4 minus y squared minus this thing to the fourth is going to be 4 minus y squared squared minus 2 times 4 minus y squared. Square that, and you're just going to get that times y squared plus and square, we're going to get 4 minus y squared times y. Okay, and all of that now minus, and notice this is an even function in terms of x. So when we plug this in and it's negative and we square them, we're going to get exactly the same thing. So 4 minus y squared minus 4 minus y squared squared minus 2 times 4 minus y squared times y squared, and then plus, oops, didn't give myself enough space, 4 minus y squared times y. Everything cancels and you simply get 0. Isn't that nice? Okay? Sorry if you couldn't see the last part I was writing. Okay? But you plug this into here and you plug this into here, and because all of these x's are squared, they're even functions, when you plug this in and when you plug this in, you get exactly the same thing. So we get this, and then we're subtracting the same thing, we get 0. Okay? So what we just did is we showed that the flux through this surface is equal to 0. So now to verify that the divergence theorem actually works, now we have to do the other part. Okay? So if you go up here, we're going to do this side. We're finding the triple integral of the divergence of f over the entire volume. Okay? So let's find the divergence of f. Remember what f is. F is 2z, x, and y squared. The divergence of f is equal to del dotted with f. Okay? Which means we take the x derivative of this plus the y derivative of this plus the z derivative of this. Oh, well, isn't that interesting? So we're doing the d dx, the d dy, and the d dz. And we're dotting that with this thing, 2z, comma x, comma y squared. So the d dx of 2z is 0. Plus the d dy of x is 0, plus the d dz of y squared is 0. So we're taking the triple integral of 0 dv, and we get 0. So we have confirmed for this case that the divergence theorem actually works.